Hi, everyone. It's a pleasure to be here and to introduce this work that I've done on computational harmony. A couple of words about myself. I'm a machine learning engineer in Autoregressive technologies. This work has been done, however, previously while working as a postdoc in the algorithms team at the University of Lille and as a machine learning researcher . Hi, everyone. I'm very happy to be here to present this work that I've done in the past. A couple of words about myself. I am a machine learning researcher in Autoregressive technology. And this work has been done previously while I was a postdoc in the algorithms team at the University of Lille and a machine learning researcher in ByteDance TikTok. And has been presented a couple of times in a couple of papers already in the past. So I'm going to give you the references to this paper just very soon. The talk is about computational harmony and especially how to approach a complex musicological problem with machine learning. What I'm going to do is talk a bit about what we've done and show results of what we have done and try to sort of generalize what I say here and show what could be other different approaches to it and how it could be the same techniques that we're using could be adapted to different kind of problems. Our work has been done with symbolic music in mind, which means MIDI files or music XML files. It is adaptable to audio files with the due modifications I'm going to mention a bit later. So let me go directly with the outline of the talk. There's going to be a very short musicological part about what's harmony, about the harmonic analysis and Roman numeral notation, and what a musicologist would do to solve this problem. Then there's going to be the technical part about the machine learning model that we use, and finally the conclusions where we look at the results and some examples if we have time, and you can ask me questions after this recording is ended. Okay, let's dive into it already. Let's start by listening to some music since we are talking about music. This will allow us to actually present what we are doing. I'm going to start this clip now. You can follow on the score, alternatively the melody and the harmony. Okay, this short excerpt to show that we have here two parts to this music. This is a music in a sheet music notation or fake book notation. It has melody and harmonic line. The harmonic line is written just with chord symbols. In this case, the chord symbols of this first part are A flat, B flat 7, B flat minor 7, E flat 7. If we go to a different example, there is another music notation, another different piece that are not listening now, but you will be able to find it in the slides following this link. So we can see that the harmony here follows B flat, C minor 7, F7. This looks very different from what we had in Take the A Train, but if we look to it more closely, and if some of you know a bit about music and music theory, you can see that there is the same distance between roots, and so it means that the chords have the same function. What I mean by distance between the roots is the number of semitones that are in between these notes. So between B flat and C, there are 2 semitones. Between A flat and B flat, there are 2 semitones. Same between C and F, there are 5 semitones, and between B flat and E flat, there are 5 semitones. A semitone is the smallest distance between notes on the piano keyboard. So the fact there is a lot of music theory behind here, and it's not really important for you to understand it now, but the fact that there is the same distance between the roots of these chords, it means that they have the same function inside the music, so that we could play I got rhythm with these chords and lowering the melody as well, and we wouldn't really notice the difference. It would still work. It would be still the same song, basically. So how can we, our goal basically is to, given a score in a complete sheet music notation, to be able to obtain these chord symbols notations. How can we do that? Well, we pass through Roman numeral notation, because that's what highlights the different functions between chords. And the Roman numeral notation is this kind of notation that I'm going to explain very briefly here. So a chord symbol, for example, in this case is E minor, showing that this contains the note E, G, and B. And imagine the key is E minor as well, then this is written as, in Roman numeral, as key of E minor, first minor chord, because the first note in the key of E is, of course, E. And then if we do some changes to this chord, you can see this both chord symbol notation, Roman numeral notation changing, etc., etc. But there are some cases in which, for example, the chord symbol notation changes, but doesn't change, but the Roman numeral notation changes. So there is some, some mapping to do between the two. The advantage of using this Roman numeral notation is that it allows us to actually highlight the similarities between these different songs. For example, in I got rhythm and take the A train, in both cases is 1, 2, 7, 5, 7. The only things that change is the key. So basically, the Roman numeral removes the absolute information on the notes and just gives a relative information on the notes of the roots of the chords. So how does a musicologist do analysis and harmonic annotation? They take the score, they identify which key is the score in, they segment the chords. Like here, you see one chord in the first bar, another chord in the second bar, another chord in the third bar, etc., etc. They assign chord labels by looking at the notes that are in each segment, and then they study the progression between chords and do their statistical or musicological analysis with those. And this works very well until the piece is simple enough. If we go to slightly more difficult pieces, well, this becomes very complicated, because identifying the keys really complex, because there are, for example, modulations. So in order to identify the key, one needs to study the progression of keys, actually. Then segmenting the chord is difficult, because nobody tells us where are the segments. It's something that we have to do ourselves. And also there are non-harmonic tones like this ones and this one that do not belong to the key in which the P is written. And they are just passing notes that embellish the melody, but they don't have a functional harmonic function. So segmenting the chords and assigning chord labels is quite complicated in this kind of case. And there is no known algorithm that musicologists can use in order to do these kind of things. As a matter of fact, different musicologists often interpret the same harmonic annotation in different ways, so they could write different things here. An example here is this question mark on German 6/5, because there are several different possible annotations here that are equally valid according to the sort of way that you want to interpret the music. And so it becomes a mess to try and approach this problem with a rule-based algorithm. So what do? Well, we try a different approach, machine learning. So in order to try machine learning, we have to transform music into some purely mathematical data. And we take a look at the problem from an abstract perspective. So let's look at it. The input data is a score file. So it's a long sequence of tokens. And this could be both audio and symbolic music. For example, when I say score, it could be a recording or a MIDI file or a music XML. In any case, it's a long sequence of tokens. A token could be, in the case of audio music could be simply a sample in the WAV or MP3 file, and in the case of symbolic music, it could be a note or a duration or the alterations or the whatever it is that we have in a score. The output data is also a long sequence of tokens, and these tokens are, in this case, the chord annotations. So in Roman numeral, for example, 2/7 in the key of C major. The alignment between the input and the output is of the utmost importance, because if you just imagine somebody that starts a song, and if the singer doesn't enter at the right moment, so if there is no perfect alignment between melody and chords, it's extremely noticeable. So it's very important that there is perfect alignment, differently from, for example, what happens in neural machine translation, where the alignment between the input text and the translated text is not that important because they can have different length. So at every step of the sequence, we have an input of symbols are active at that moment, for example, and we have an output of these chords are active at that moment. So this is a classification problem, because the chords, they have a limited dictionary, and we have to choose inside this dictionary what is the best chord at each moment. So we have made a analysis, an abstract analysis of this problem. There is no rule-based solution, and the way we are approaching it is in these 3 steps. The first step is feature extraction, then there is sequence learning, and then there is classification. These are the 2 references of the 2 papers that I published previously with other colleagues, talking about going in detail into this stuff that I'm going to discuss following this. Feature extraction. What's feature extraction? When we start with a music score, it does contain all the information, but it's hidden there somewhere. It's hidden for us, and it's hidden for the machine learning algorithm as well. So what people do often is they know that there is some better way to actually represent the data that is not what the data is stored in order to do the analysis, and so they extract these features from the initial data in order to facilitate the task of the machine learning algorithm. And an example of feature extraction are piano roll notations, spectrograms, MFCCs, or there is more advanced feature extraction that could be even learned by the machine learning algorithm itself. That could be, for example, CNNs or autoencoders encoding parts. So it is difficult sometimes to draw a line where the feature extraction finishes and sequence analysis starts. And by sequence analysis, we mean like the studying the succession of these sequences of features, and understanding how they correlate among them, like how feature at time t is influenced by the feature at time t-1, t-2, but also maybe even t+1 and t+2, since we do not really care about having a real-time algorithm here. We can use information from both the past and the future, so we can do it bidirectional. In our case, we use a piano roll notation. Piano roll notation takes a MIDI file and quantize the time axis. Quantization is arbitrary. In the case that we've published, it's 1/32 of a note, which is a very short note in written music. And long pieces are actually often split in shorter chunks, and the chunks are analyzed separately because we do not really need to know what happens in 100 measures from here or 5 minutes from here to understand what is the harmony at time t. And it uses a multi-hot encoding. It's not one hot because it's possible to have several notes playing at the same time, so we need to leave this possibility. Standard piano roll notation has some drawbacks. For example, it's non-invariant for octave transposition, and music is pretty much similar to itself when you transpose it an octave higher or lower. It doesn't introduce pitch spelling. That is a more advanced music theory concept for which A sharp and B flat, while having exactly the same audio representation in most cases, they are not the same note from the theoretical perspective. And it also has other drawbacks like notes that are, we don't know if notes are held or repeated. So we proposed some modifications to the standard piano roll notation. And we derived this kind of notation in which we have, as you can see, two different sets of pitches, basically. One is all the notes rescaled by octave and introducing pitch spelling. And the other one is just the bass note. Why do we keep the bass note separate? It's easy to understand that the bass note is the most important note from the harmonic perspective, because if one takes the physics of music, the bass note has the lowest frequency, and so the harmonics of the bass note are the one that have to be matched by the harmonics of higher notes in order to give a consonant sound. And in classical tonal harmony, this is often respected, the harmonicity of the sounds, with some codified exceptions. So the bass is very important to annotate. So we decide to explicitly tell the model this is the bass, instead of the model trying to understand the importance of the bass on its own. Then after this, there is a learned step of feature extraction using a CRNN. So we use a CRNN where each times it's a one-dimensional CRNN where there is time on this one dimension of beta set frames, and on the channel dimensions there are all the different notes that could be played at the same time. And feature extraction basically looks at neighboring frames and tries to find out what are the correlation between these kind of frames. And in our perspective, would be able to say, okay, that for example, there is one note and the fifth of the same notes, they are played at the same time there. So feature extraction would be able to recognize these intervals, the most famous intervals, and actually highlight them individually. We decided to make it learned because this is a combinatorial problem, so there could be lots of different intervals that can be useful. So we decided to let the machine learn what is the most useful to them. What we actually use here is DenseNet. DenseNet is a advanced version of CRNN that uses skip connections, and that uses some bottleneck layers and some ReLU and batch normalization, etc., etc. If you're interested to know more about DenseNet, you can follow this link. And then there is sequence learning. So sequence learning, there are lots of algorithms for dealing with sequences. For example, LSTM, GRU, sequence to sequence, transformer, etc., etc. We use GRUs in a model. GRUs are a kind of recurrent neural network in which there is a hidden state, and the hidden state is propagated through time through an additional weight matrix that is indicated here with W recurrent, and it's updated by both the previous state and the new input, and at the end it can give an output here. In this case it's Y. This representation here is giving a many-to-one correlation. What we actually use is a many-to-many, where we have one output for each time here, time frame here. GRUs is slightly more complicated than this very simple recurrent neural network, and I strongly suggest you to follow this, to read this blog post by Christopher Olah that is extremely well written and that explains all the different situations with very neat diagrams and clear equations that highlight everything. I'm not gonna go into the details of GRUs or LSTM for that matters, but know that we use a bidirectional version and that it helps us to analyze long-term correlation between different frames. So convolutional neural network analyze short-term correlations and identify what are the local features, and recurrent neural network GRUs in this case analyze long-term correlations and understand like basically the key and what is a higher order structure of the harmonic structure of the piece. Finally, there is the classification part, which is the core of the problem. The problem here is that the dictionary, the vocabulary of chords is extremely vast. For example, even if one takes into account a simple model, there are more than 600,000 different possible combinations. So a 600,000 way classification algorithm is extremely cumbersome to train and very difficult to understand, especially considering that we have more or less 100,000 annotations of chords. So, well, we augment this data with data augmentation, transpositions, etc. But still, you understand that it's not really extremely easy to do this kind of to learn such a complex classification. So people do several different things. What I'm going to talk about now is a way in which we do multi-output classification. So we have 5 different outputs plus an additional output that is the root of the chord and can be derived by these 5 outputs, but we predict it independently. And each of these outputs is has its own softmax. So the total size becomes a sum of this, so around 100 instead of 600,000. So it's a definitely manageable problem. And we do introduce a thing that is called a, let me skip this. We do introduce a thing that is called the NADE in order to introduce correlation between the different outputs. NADE stands for Neural Autoregressive Distribution Estimator, and basically does a sort of ping pong in between a hidden and a visible layer, and these are determined. Both of these are determined. The bias to both of these are determined by the denseNet plus GRU layers that we discussed before. And what the NADE does is to determine first the key, and then use the information of the key to update the hidden layer, and then determine the degree, and then update the hidden layer with the information on the degree, and then determine the other steps out of the model, so that it introduces correlation in between the different various outputs. And this makes the third part, and probably the most unusual part of this model, the one that maybe not many of you have heard about. I encourage you to read this paper and the references therein to discover more about NADE. I really like this architecture, so I'd be happy if more of you would study it and would introduce it in different situations and different papers. These are the equations governing NADE, in which you can see this ping pong in which x is determined by h and h is determined by x. Let's take a look at the results, for example. So blue results use transformer in order to tackle the complex problem of having hundreds of thousands of different examples of different classes. The one on the left is a network that has 5 different outputs, but doesn't have NADE, and the dark red is the same one as the one on the left, but introduces NADE. So as you can see, the introduction of NADE has a very big impact, especially on harder tasks like finding the entire Roman numeral notation, including the key. So it's the most difficult task that we ask the system to do. We have a relative increase in accuracy of almost 20%, which is a great result. Especially I want to point 2 things that we noticed. First one is what we call the root coherence. So as I told you before, we predict the root of the chord, but the root can also be derived by the other features. And we checked when these 2 different ways to obtain the root are consistent with each other. And we found that without the NADE, this happens in 79% of cases, and with the NADE, it happens on 99% of cases. So it's almost every time it's really coherent. So really NADE works as intended. The other thing I wanted to discuss is the key oracle. So basically, if we, at prediction time, if we are able to tell the model what is the real correct key of the piece that we are trying to analyze, which is an information that is not super hard to obtain, then the quality of the harmonic analysis increases much more than we would expect with a model that doesn't have the NADE. Once again, NADE is great architecture, so I encourage you to explore it. Very briefly, there are more things that one could analyze. For example, the keys, and you can see that the key prediction is quite good because the main diagonal is the correct key prediction, and these off diagonals are musically understandable mistakes or ambiguity, let's say in some cases, between different keys. So of these diagonals, there is almost nothing. Good to know. And I'm gonna skip these examples. You can find them. Please feel free to ask me about all these example types of errors that can happen in our problem. This concludes my intervention. Thank you very much, and talk to you soon.
Okay, Gianluca, thank you. That was a really interesting presentation.
Thank you.
I think we have some questions from audience. So the first question is, given the small number of labeled data, have you considered using an unsupervised learning approach in your work, similar to that used in language modeling?
Yeah, so of course we try to think about it, but it's not always easy to find a non-supervised learning algorithm that can adapt to all the use cases, and we didn't manage to. And up to my knowledge, there is no such algorithm that has been published in the literature. Everybody is just using labeled data at the moment.
Okay. So there's another question. Have you thought about using pre-trained models in your work? Are there any particular ones that could work well? If not, why?
Okay, so for using pre-trained models, actually, yeah, we did consider that one as well. The point is that, well, there are not many pre-trained models in harmonic analysis specifically, and of course one can use pre-trained models that have been, for example, we thought about using Jukebox, OpenAI's Jukebox model that is able to basically represent the data into an auto-encoded version, and so starting from that feature representation to do harmonic analysis. Or there was something that has been proposed by Stefan Lattner about doing some relative representations of music. So basically, the part of feature detection, yes, we thought about using a pre-trained feature detector to do our work, but in the end, we didn't really have time to explore that avenue as well. But this is definitely future work to do.
Okay, thank you. I believe that's all of the questions. So thank you once again for your presentation and your answers. Thank you very much for being with us.
You're welcome. Thank you.